Hello. This is my attempt at a workshop for Android Exploits 101, and my name is Maddie Stone. I am a security researcher at Google Project Zero, where I focus on zero-day exploits that are actively used in the wild. So not the ones that are hypothetical or a bug report by a VRP, but the ones that for some reason there's indications or evidence to suggest that attackers are actively using these exploits against folks. And this is my co-instructor, Bug, but he's sleeping on the job. So we'll just pretend that he's, taking part. So the goal of this workshop and why I put it together and created it was to help share an understanding, and that y'all will come away with an understanding of what is the shape of a modern zero-day exploit for Android. Because most of the stuff that's out there right now actually talks about exploits from 5, 7, 10 years ago, which what's required to exploit Android today is very different than what exploits look like back then. So I also hope that you'll walk away with a foundational understanding of current exploit threats to Android users. And maybe this can inform investments in defenses and detection, and how do we protect people from this type of exploitation. Lastly, I hope that you just see how fun this is, and maybe you even want to join in on the work. So as I said in bio, I work on zero-day exploits that are actively used in the wild. So my goal of the work, the program, everything I've been doing for the last few years is that when zero-day exploits are detected in the wild, that is the failure case for attackers. And thus we need to do everything we can to learn from those, because that's what's going to ground all of our data and beliefs and choices in some ground truth of what is actually happening versus what we think may be happening. So through this, there's a couple different resources, references I have if this information is overall interesting to you. We have a tracking spreadsheet where we try to track known 0 days, or known in the wild 0 days. We also have a public repository of root cause analyses where welcome any and all pull requests. The goal would be to have those for every in the wild 0 day. 2021 has been quite the year, so not quite. But yeah, as well as for the last 2 years, I've written year in review reports of what we can take when we put all of the instances of detected in the wild exploitation, 0 day exploitation together. Lastly, did a keynote for OSCERT this year, which I think really wraps up a lot of this work in a video. But let's make sure we're all coming from the same definition. What is a 0 day exploit? I'm defining it as an exploit that defenders don't yet know about, or a 0 day vulnerability, a vulnerability that defenders don't yet know about. So this is different than end days or spam or abuse. End days being bugs that are already known about. They may have a patch available. Someone knows about them, so they could be antivirus signatures, things like that. 0 days, we have none of that. And 0 days is that niche that I'm specifically focused on. And yeah. So here's an example of a RCA, a root cause analysis that I mentioned earlier. So you can follow that link to the repository. So here was one done by one of my team members, Ben Hawks, earlier this year on the Qualcomm GPU. And I just include this here for an example of what this looks like. Our goal is that this is a central repository for facts about the 0 day. So where can you find the information, the advisory, what versions it affects? If it's open source, the patch CL or the bug introducing CL if found available, etc. We also then go into the basic foundations of what's technically interesting about that 0 day. So what is the vulnerability they're exploiting, and what is the exploitation method? From there, once you have that baseline data, we then provide some suggestions. How could you detect other 0 days similar to this? How might the attackers found this? What type of variant analysis could be done? Because the thing is when you find one vulnerability, you often find more than one. So the attackers were using one in this case. What other ones may they have as well? So that's what those RCAs in that repo is for. But let's get into Android and what's the shape of it. At the very basic level today, when most attackers are not going to sit there and be like, I want a 3 0-day exploit chain for this device. That's not usually how the goal comes about. Instead, they say, I want a remote full compromise capability for this device. Today, for an Android, that often means they'll need 3 different 0 days chained together in order to have that operational capability for remote full device compromise. So the first one would be a browser renderer, remote code execution. The second one may be a sandbox escape from the browser. And the last one, the local privilege escalation. This is generally the most broad sort of breakdown of the shape. So the goal, I think next 45 minutes, an hour, is to really break down, though, what are those specifics for Android? What may that look like? What options there are? So we can talk about what these 0 days, how maybe we could better detect them, how we could better defend against them, how can we better understand how they're being built, etc. So I created this chart to try and lay out visually what are the options for getting that full remote compromise of an Android device. And as you can see here, there are quite a few options. So for me, this just helped break it down of where might we better detect and where might be better defend. Oh, because I meant to mention this in the intro, but my expertise is generally 0-day exploits that are exploited in the wild or actively used in the wild. I do not view myself as an Android expert, an Android kernel expert, GPUs, Chrome browsers, etc. So I put all of those caveats out there. But I did not see material like this out there, and I know that it was useful to me. So I put it together, and hopefully it's useful to you as well. So this was the graphic I made to try and lay out as I'm trying to think of what are new ways that we could better detect Android 0 days. And so the goal, and over this next time, is we're going to walk through each of these with some examples, my thoughts on the difficulty around them, why we haven't seen them, maybe ideas for detection, and all that good stuff. So first, we're going to start up here in the top corner. This is maybe this is one of the main ways we may see attackers try to get onto the device first, either via 0-click, meaning no user interaction, or 1-click, meaning they clicked a link or answered a phone call or something like that. And so this first one is they have some application exploit, which gets them remote code execution within that application. So most user-installed applications are running as the untrusted app SE Linux context. So that's what we're going to talk about as this first step. And so most of those application exploits, the reality is they're largely going to be in messaging or video conferencing apps, because messaging and video conferencing apps make a great 0-click attack surface, meaning a remote attack surface that doesn't require user interaction. So that's what attackers would really like to have, because you don't have to have the target do anything. You just have gotten that first step of code execution onto their device. So for video and audio conferencing, WebRTC is generally the most common library that's used for that. And so as a note, most Android apps will have this conferencing and messaging code in a native library. So while Android apps are largely written in Java or Kotlin or language like that, this type of processing code, the conferencing and stuff like that, is largely within those apps as compiled native code, meaning compiled C, C++. That also means it's now opened itself up for memory corruption vulnerabilities as well. So in terms of the messaging video conferencing space, there are tons of messaging and video conferencing apps on Android, lots of different options. So there's Android Messages, which is that generally the built-in app. You have Google Duo, you have WhatsApp, Signal, Telegram, WeChat, and on and on and on. And what it seems like is based on generally the geographic region or who folks are targeting, which app is of interest and targeted tends to be what population is being targeted. So we have one semi-recent in the wild example, which was a WhatsApp 0-day allegedly used by NSO Group, was a zero-click CVE 2019-3568. And there's a great checkpoint blog, as well as I did a conference talk on trying to patch diff this vulnerability and figuring out what it was. As well as non in the wild, but my teammate Natalie Silvanovich has written so much great blogs, research, resources, etc. on finding vulnerabilities in Android messengers and video conferencing and stuff like that. So here's one of her great blog posts of exploiting Android messengers, as well as my other teammate Mateusz Czorczyk wrote a detailed series on an exploit chain for Samsung devices via MMS. And so that one's really cool because that's another, remote full compromise, and he really walks through step by step how with MMS being that initial attack vector. So the other attack vector, if you're not using a messaging app, is often a browser. Most notably for Android, it's going to be Chrome, or many of the other browsers you may find on Android are also built on top of Chromium if they're not Chrome. So Chrome uses this multi-process architecture. So they have the browser process, which is sort of the main privileged process. Each, you could say, tab is generally in a renderer process. So that's where any content from the websites is executed. And these are that more isolated sandbox process are each of the renderers. So when we're talking about the steps, you're going to have that render. An attacker first needs a 0-day to get remote code execution in the render, and then they're going to try and escape the sandbox. And that's when we're talking about where they're trying to get footholds in the browser process or the GPU process, which is also privileged. So these are the two boxes on this graph that would represent the Chrome processes. The purple one at the bottom that says Chrome isolated service renderer, and the highlighted box right now, this one. So that's that render isolated sandbox, not many privileges, one where the website contents are executed. The green box will represent both the browser process and the GPU process, because both of those are privileged processes running as that untrusted app context. So if you were to have Chrome open on your Android device, run PS to see what processes are running along with their SE Linux contexts, this is what you would see. So we have that, most privileged browser process. It's just com.android.chrome. And we see that it has the SE Linux context of untrusted app. Then Chrome also has an app, Zygote, however you pronounce that, process, which manages all the different isolated app renderer process, all those sandbox processes. This app Zygote process manages all of those. So something that has become very much of interest over the last few years, just because we're seeing for both security researchers and in the wild attackers are targeting it, is the GPU process. So on Android, if you run PS and are looking for it, it's actually called the privileged process, not GPU. And that's because it actually has the same privileges as the browser process. We can see in the SE Linux context here that they're exactly the same. And so this is why I think, more attackers are finding this a promising foothold and using this as a way to break out of the sandbox, not just going for the browser process. So first, we're going to talk about some render remote code execution. What do 0 days look like? What do exploits look like that for that first step of maybe they sent a link or they managed to get a redirection to their malicious website or exploit server. So the first step is getting render remote code execution in that sandbox process. And so, so gaining remote RCE, remote code execution and render is usually the first step. And the interesting thing about the render exploits is they actually tend to be usable across the different platforms. So when it gets into sandbox escapes, like those are often different based on, is it Chrome running on Windows? Is it running on Linux? Is it running on Android? Those sandbox escapes are not necessarily interchangeable. But for render, we're generally seeing the same ones used across those platforms. So the common targets of a render RCE 0 day is V8 is about the top because that V8 is the JavaScript engine that Chrome runs on. And so that's where a lot of these render 0 days are. The next most common would be Blink, which is the DOM in Chrome. And finally, fonts. So fonts are still a viable attack target. And those can be especially interesting because if you find a font 0 day in one of the common font libraries, then it's actually even more useful to you because it might be that both, say, Chrome and Safari use that library. And so now you have a 0 day for multiple browsers and not just one. However, the thing about these render RCEs is they're still primarily memory corruption bugs. So attackers have not had to really update, come up with new bug patterns, come up with new, maybe tougher to find logic bugs or something like that. We're still, memory corruption makes up the majority of what we're seeing. So here are a few different examples of in the wild Chrome render RCEs that we've seen last year and this year, along with some write-ups about them. And I think we're going to walk through in detail one of these. Oh, first, this graphic is from a blog post Project Zero published, I guess, earlier this year about a exploit server discovered in October 2020. And I highlight this mainly just because what we see here is, so the Chrome render RCE used against Windows was the same Chrome render RCE used against Android. And so that's just, while they run different architectures, largely the same exploit could be used for both. But that's not the case once you get to this next step of sandbox escapes. So let's talk through one of these in the wild bugs in detail. So this is CVE 2020-1599, which was that one that was used against both Windows and Android and Chrome, and it was actually in the free type fonts library. So it is a buffer overflow due to integer truncation here in this function load sbit png. So what's going on is, first we read the PNG's header to get the image width and the image height. These are 32-bit integers here. But then right here, we see that that image width and that image height is truncated to a short, or 16 bits. And that's what width and height are populated with. So down here now, they need to allocate a backing buffer that's going to be used for loading this PNG data. But what we see is that they're actually using the 16-bit truncated values for generating that size and that size of that allocation. But, and while it had to be ellipsicized, is that a word? It should be, because it's fun to say ellipsicized. Out here, that backing buffer, that is generated or allocated using the truncated size is in this PNG struct down at the bottom, and we are reading in based on the untruncated data. And so thus you get that buffer overflow, a pretty conventional pattern. So that is an example of an in the wild Chrome render RC. So the next step, you have that render, you have that code execution in the isolated Chrome process, meaning this box, purple box here in the middle, this is Chrome isolated service. The next step is we need to break out of the Chrome sandbox. And it turns out we actually have quite a few different options for that here on Android. So our first option is we can break out by going to either the Chrome browser process or the Chrome GPU process, which both of these are this green untrusted app context box because they're both running as the untrusted app SE Linux context. Or we actually have two more options as well. We could follow Chrome isolated service to a subset of the kernel syscalls and directly find a privilege escalation rule, which will also allow us to break out of the sandbox there. So this small subset of syscalls that are accessible to that isolated render could give us that option to break out of the sandbox. So Binder, the inter-process communication mechanism within Android, is generally the best example of that because it is accessible from the Chrome renderer. The last option is similar to the kernel. There is a small subset of system services that are also accessible to the isolated renderer. So that is another option for Sandbox Escape. So to put this in words rather than imaging, as I said before, when I'm saying Sandbox Escape right now, I'm meaning escaping that Chrome sandbox of the isolated app process rather than the general application sandbox. And so I mentioned we had 4 processes for getting that escape when we have render RCE. So render to browser process, render to Chrome GPU process, render to kernel, which generally is Binder is that subset that is accessible, some file system stuff too, or render to system services, a small subset there. So we have a few different examples here. CVE 2026-572 is one of the in the wild examples, and we're going to go look at it in a little more depth. We have CVE 2020-1601, which was another sandbox escape to the Chrome GPU process. And lastly, a sandbox escape via payment processing code as well. So let's talk about CVE 2020-572. So it was a use after free, another conventional memory corruption, and media codec audio decoder, the destructor. So this in the wild vulnerability is actually a variant of 2 previously known vulnerabilities in the same code, also similar patterns, and those other 2 have been reported by security researchers. So what this is it is Android-specific code in the Chromium code base. So this code only executes in Chrome on Android, not in Chrome on other platforms, because it is the code that calls into Android's media decoding APIs to support the playback of DRM-protected media on Android. And so this is running in that Chrome GPU process, the privileged process. So that was, an interesting and as privileged as the browser process type of attack surface. So what's basically going on, a unique pointer is assigned to another, which means it's deleted because it goes out of scope. But at the same time, there is something holding that original reference something holding the reference to the original object via a raw pointer, and thus you get the use after free. So this one, we do also have the full RCA up on, up on our root cause analysis repo. Here it is, also linked here. So if we want to think about what does Chrome look like in the context of full chains, how are they connected? How did the different pieces work together? There have been a couple of really, I thought, great write-ups. The first one is by Manu Mo of GitHub Security Lab, and he's done quite a few of these, but this one is going from a render RCE in Chrome Web Audio to the Sandbox escape in Chrome payment processing to a vulnerability in Qualcomm's GPU driver for that final privilege escalation. There's also a Project Zero blog post talking about what we saw in the wild, as well as Guanggang did a great talk at Black Hat 2020. And so we're actually going to talk a little more about it because I think he did some great graphics, some great work, and it's a good example too. So this is from Guanggang, and it is, he called this Tiyun-song. I'm sorry if I mispronounce it, but this graphic is amazing. So what he started with for a full chain, CVE 2019-5877, which is out of bounds access in V8. And so we can see by his diagram here that this is the render RCE, and it is firmly inside the Chrome sandbox. And then we also see this larger dotted line, which was the Android application sandbox. So next, after you have that render RCE, we need to break out of the Chrome sandbox. So via Mojo, which is the inter-process communication for Chrome, he had this use after free, which this is the one that was also in the media codec audio decoder component. And he breaks into the Chrome privilege process, the GPU process. So we're still inside that Android application sandbox. We've broken out of the Chrome sandbox. And now you need to get a privilege escalation. And so from here, you can get a system call to via a bug in the Qualcomm GPU driver, and thus get to the Linux kernel. So I thought this was a great diagram showing sort of the different processes. Highly recommend the video, as well as I have the white paper linked a little later on in these slides. So we've broken out of the Chrome sandbox, or we got execution via a messaging app exploit or something like that. Now we want to get privilege escalation on the phone. So when we're talking about LPEs, Priv Escs, we're usually talking about any of these three boxes on the right: system services, GPU, or the kernel. So for privilege escalation, largely most attackers are going to be trying to either get to root user, which is the most privileged UID on the device, or maybe it's sufficient for their needs to get to system, which is the second most privileged user ID or user on an Android device. So system services run as system, and that's why they may be a target or attack area for LPs. So this write-up is from my teammate Ben Hawks on a blog post he posted in 2020. And I just thought this was a really great way of sort of framing out the Android ecosystem. Because folks generally talk about, is there an Android 0 day? Mm-hmm. But that doesn't really have the meaning I think we try to make it mean when we say Android 0 day now. Due to fragmentation in the ecosystem, there's thousands of OEMs, you know. It is very, very rare to have a 0 day that will affect every Android device. So there were a few, you know, back in the day, but it's just really not all that common that attackers or security researchers can have enough confidence to be like, oh yeah, this will affect every Android device. So this ubiquitous tier is not really where we're at today with modern Android 0 days. So the next best option in terms of return on investment, if you want to have a capability and exploit for the most amount of devices, is chipset. So these are the 0 days that affect a large portion of the Android ecosystem, because they're based on whatever hardware is used by various OEMs. So the biggest example right now and most topical is going to be GPUs. There are largely just two different GPUs used within the Android ecosystem. One is the Qualcomm Adreno and the other being the ARM Mali. And so there, now if you find two 0 days, one in Qualcomm and one in the ARM Mali, then you can basically have LPE capabilities across the majority of Android devices. Some other examples might be, he has listed here the Snapdragon SOC perf counter vulnerability or Broadcom Wi-Fi firmware. So yeah, that's what sort of these chipsets and why we might be seeing so much more targeting of GPUs for LPEs. The next step would be vendor, which that's going to be, you have a 0 day, you're pretty confident affects all phones or devices from this specific vendor, whether it be, Google for the Google Pixels or Samsung or Xiaomi, Huawei, whatever you're talking about. Lastly is, and it's probably the option folks want least, is a 0 day that only affects one specific device type. Yeah, and so I think as a very side note, just for my personal thoughts of, I think this is an example of why absolute counts of 0 days are not that effective of a measure of security, in the sense that there are going to be more 0 days, absolutely, if you need more to target the same portion of the ecosystem. And I don't think that is necessarily better, worse, etc. I think it's just a fact, and it's something I've sort of tried to change my mindset around of what does it mean to have an Android 0 day? And that's actually of, okay, chipset wise, that might mean you have to have two if you want to have that Android wide capability, or things like that. So first, let's talk about system services. I actually, there's not a ton of data. We don't have any in the wild knowledge about system services 0 days. But to start at the basics, system services are services that run in the system server process, which runs under UID system. So generally second most privileged user ID, as I said before. And you can think of these services as the things that are sort of required for that basic functionality of the phone. They're built into that Android framework. So it's things like, telephony, package manager, activity manager, power manager, battery manager. You get the gist. And so the examples I was able to find is one from 2018 in this blog post from Zimperium, as well as deserialization vulnerabilities are usually going to be over here as well in the system services. Kernel. Yes. So one thing I think I've gotten ahead of myself that I don't think I've mentioned is, so it is October 19th, 2021. And since 2014, there are now 6 total known in the wild vulnerabilities for privilege escalation that affected Android devices or targeted Android devices. So that is not much. So the first one was in 2019 that I worked on with some teammates, and we found quote unquote bad binder. So that was a kernel one. And then there have been 5 this year. And all of those 5 are in the GPU. So I want to preface this, that part of the reason I ended up creating this is because I was like, we need better detection of Android 0 days. We know what's happening. How can we go about detecting even better. And so that's what sort of this came out about for me trying to create and share with folks to get more brains thinking about the issue. So that's all to say that we don't have a lot of data about in the wild and what attackers are doing to target Android phones with 0 days. And so that's where, there aren't any in the wild examples for system services. And we're going to have one to talk about for kernel. And even in that case, the actual exploit sample was not found. So yeah, let's get into it. So kernel Priv, that's generally what most folks are thinking of when they're talking about Privesks on, an Android phone. So again, don't have a lot of data for in the wild for this. Thankfully, there's quite a good amount of security research and published research, which we can go off of. But yeah, only one example for actual 0 day in the wild. So first, there has been in the wild use of in days. And so I still think this survey that my teammate Mark Brand wrote of a survey about in days used in the wild was really interesting as well. Obviously, the goal is always to force attackers to have to use 0 days rather than in days if they're going to have success, because 0 days are much more expensive, much tougher, require more resources, and we want to make it as hard as possible for folks to, or hard for attackers to be able to exploit folks. Kernel drivers is one of the common ways, as well as syscalls, is how folks get into the kernel. But generally, the most ripe attack surface has been binder, which is that inter-process communication. And it's especially interesting because it's accessible from the Chrome renderer. That isolated app process can still access binder. And so the in the wild example we have is CVE 2019, 2020, I can't talk now, 2215, which, because everything needs a name, was named bad binder. And so I did a blog post as well as a video about that. Again, no one detected a sample of it. Instead, it came from information about exploits for sale. And so that's still that's not what you want to rely on for detecting exploits. It's always nice, but we want to be able to detect and find the samples and find the exploitation. The next one is a non in the wild, but a great blog post, I thought. It's from Blue Frost Security. And it's an interesting example of how with that 1 0 day in binder, they're able to use it twice instead of needing 3 0 days. They're able to use it as both the sandbox escape and the privilege escalation to root. But the GPU, which is, it's time to shine or something. We've had 5 known in the wild 0 days targeting GPU drivers so far this year. So yes, there's the 5 this year in the wilds, as well as we've also seen beginning last year a lot of security researchers who try to develop exploits for Android beginning to target the GPU as well, the GPU driver as well. So as I said, there are 2 main GPU drivers for all of the Android devices, the Qualcomm Adreno or the ARM Mali. And here are some great write-ups. So CVE 2021-1905 was a in the wild bug that was patched January of this year. And so there is the root cause analysis for that. Ben Hawks also did an interesting blog post about his attempts to attack the Qualcomm Adreno, and his success, his experience, let's put it that way. The Guangang's presentation from 2020 that I showed y'all the graphic earlier of, as well as there was this interesting talk I found from Black Hat 2016. So we've now covered the main routes we're seeing attackers use for to have a full remote capability to exploit Android devices. Now we're going to talk about some routes that we know are of interest, that we have anecdotal evidence that's being used, but for reasons, as we will talk about, are really, really hard to detect. And so there are no known in the wild cases of it yet, and thus just not as much research. Oh, Bug woke up. Hi, Bug. Right there. So first, let's get into Wi-Fi, NFC, and Bluetooth. So why are these so hard to detect is, well, they're also going to be focused on proximity, physical closeness, so not quite as easy, not that other things are necessarily easy either to detect. So if this is the input route that you are going for, then there are generally multiple options for exploitation. You can go for user mode on the component chip or exploiting to kernel mode on the component chip. You can try and go for user mode on the application processor, or kernel on the application processor. Yeah, so there's a lot of options. There's been some good research. One example I've linked here, just not a lot of information, but I include it because we know just from random talks, comments, data found that we know it's happening. And so I don't want to leave it off because who knows, maybe one of y'all have the brilliant idea of how next to defend against it or detect it. But yeah, I wish I had more to say here. And then lastly, another area I wish I had more to say is the baseband. So the baseband, the modem is, again, anecdotally, we know there's plenty of work. It's an area of interest of attackers, yet we do not have any known detected cases of baseband exploitation being that initial input vector. So poor baseband exploitation flow is usually to get code execution on the baseband processor and then escape to the application processor, usually via the baseband's kernel interface. And so there has been a decent amount of security resources publishing on this. And so here are some good ones that I thought, we've seen it used in the hacking competitions like Pwn to Own. So again, maybe one of y'all will come up with the next best way to find and detect 0 days targeting baseband used in the wild. So finding that 0-day vulnerability, coming up with a way to make that bug exploitable. Well, okay. Finding that 0-day vulnerability is only one step of the process. You still have to be able to exploit it for it to be useful. So attackers are not like, oh, I want these capabilities. They're like, or I want these different components, these 0 days with these exploit methods. They're like, no, I want this one capability. So what is it going to take to get that full remote access onto this device? And so that means that attackers do still have to find ways to get past mitigations. It's great that there are more mitigations. This is not exhaustive by any means, but it's, if we can continue to find ways to break known mitigation bypasses, because there are known mitigation bypasses for most, if not all of these currently, that adds another step to what attackers have to do. They have to create something novel, which raises the bar for who's going to be able to create, right, how much time they put in, how much they charge, all these different things to make it harder for 0-day exploitation. So with that was my very quick 45-minute Android Exploits 101 workshop. Just trying to talk about some of the basics of the shape of modern Android exploits, what we're thinking about when we're talking about 0-day chains, capabilities targeting Android devices. Again, I hope it was helpful. That's my whole goal in putting this out there, because as you can see, there's plenty of work to do. And one of the things that drives me is that these exploits, these capabilities are being used to harm people. And that's not cool. So everything we can do to try and protect these folks from this type of exploitation, I think is really important, and to do the best we can to figure that out. So yes, everyone is welcome to come and try and help the cause, whether that's jumping in and doing an RCA. There's plenty. I'm happy to help if you want to reach out to me about that, whether it's, you know, in your own roles, organizations, whatever, coming up with new detection methods. My one hope is that it will be transparently reported if reporting the vulnerability as in the wild, so that other researchers like us can all know what's going on too, and hopefully help use that as a data point to help inform future research, resources, what types of structural improvements to try and advocate for, et cetera, et cetera. So with that, yeah, I guess that's all I've got. Hope this was helpful. Bye.